So welcome, Meg, and welcome, Sarah, and welcome, Michelle. Thanks for coming in. This is actually our last Monday evening webinar in the course, because next week will be Tuesday at noon, and that'll be it. So this is our last Monday evening webinar, and it's actually like a little webinar where it's not quite as stressful as some of the last few or the next one, because we don't have a test to talk about. We don't have a project that's due this week. We're really just going to focus on statistics and not on, examinations or anything like that. So, but it is a really important piece of statistics we're doing this week. So let me share my desktop and talk about the plan. Okay, so the plan today is all about regression analysis. I'll start out with any questions you might have, but then we're going to get into the details of regression analysis. Regression analysis definitely in the top few of the most important things that happen, in statistics. It's used everywhere. Okay, so you've seen some regression analysis already. You have heard some major words about regression analysis, didn't quite understand exactly what they are. At the end of today, you still won't understand exactly what they are, but you'll understand more than what you knew before. One thing we've already talked a long time ago, we talked about scatter plots, but I want to revisit the idea of scatter plots. So we'll go more with scatter plots. And then we're going to talk about a main thing that almost everyone knows this word, but the details are different, and that is correlation. Have y'all heard the word correlation before?
Yes.
Now, can you tell me exactly what it is? Definitely not. Okay, especially if you haven't had calculus, forget it. And by the end of today, you still won't know exactly what it is, but we'll know a lot more than you did before. But you've heard about correlation, and you have maybe some ideas about correlation, and we'll definitely have more ideas at the end of today about correlation, because that's a big piece of regression analysis. Is there a correlation? In particular, we're going to be doing today linear correlation. So we're sticking to lines. That does not mean that things other than lines can't be used. You can talk about, exponential correlation or parabolic correlation, all kinds of correlations. But we're going to be looking at linear correlation, and we're going to be looking at everything about linear regression. So the letter we're going to use for correlation is R. So maybe because there's double R in correlation, I actually don't know. But everyone uses the letter R for correlation. Then, I know it doesn't seem like it's that big a deal. If you know R, you can square R and you can write down R squared. And very easy to calculate if you know what R is, because hopefully you all know how to square something, especially if you have a calculator. On the other hand, the understanding of what that number correlation means and that number R squared means, they're very different from each other. And I'll talk about, how you interpret the correlation as a number and how do you interpret R squared as a number. So we'll get into that. Then we're going to talk about the regression line. So in particular, the linear regression. So that means there's a line. And we'll talk about what about the equation of the regression line. And hopefully you all know, if you have an equation of a line, what are the two most important numbers that come up all the time in an equation of a line from beginning algebra? What are the numbers?
Y-intercept?
Good. Y-intercept is one of the really important numbers, definitely. And what's the other really important number? You all know this from beginning algebra, from basic, even getting pre-algebra a little bit. Sure, maybe you're afraid to say it, but remember? The slope. Okay, I hope you all have heard that word slope before. So when you have a line, you talk about the slope and the y-intercept. Okay. Sometimes you call it y equals mx plus b. There's two numbers where m is a slope and b is a y-intercept. Okay, so we're going to be looking at the equation of the regression line. It turns out they usually don't use m and b in statistics. It's a little complicated on the reason, but you can trust me that there is a reason. So we're going to be talking about the equation of the regression line, and we're going to be talking about how do you interpret the slope and how do you interpret the y-intercept when we're talking about regression analysis. And then a main thing is, and it's a big problem a lot of people do, is if you're doing linear regression and just analyzing the data, then you got to beware of talking about causation. That's kind of a fact in just about everything we do in our class. You really got to avoid saying that you've looked at the statistics and now we can say this causes that, because it's really wrong in just about every circumstance. So be careful about the word causation. It doesn't mean things don't cause things, but it means that you can't say that they cause it after just looking at statistics. Then, again, what would this chapter be without a hypothesis test? So we're going to be doing a hypothesis test. And this is the hypothesis test. Anyone know how to read this letter? It's not a P, by the way. It's Greek. I've yet to have any like fluent Greek speakers in my class.
Is it phi?
Good try. Good try. Phi is like a circle with a slash through it. There's no, it's not a slash through it because that line is a little to the left. So let me tell you, row. Like row your boat. So you read that as row, and it's a Greek letter. And it looks like a P, but it's actually the Greek letter for R. And that's why they use row, because correlation is R. So just let you know, we're going to be doing a hypothesis test for the correlation. And then it's really not that hard. So that is the plan of the day. It's all about regression analysis. I don't have to prepare you for a test. I don't have to prepare you for a project. I do want to let you know, I have not gotten to the project yet today. I decided to do kind of the easy one first, and that is the discussion post from last week. Those are much easier to grade than projects. And I also had, I taught a class, and then I gave a big statewide, I led a statewide seminar on the whole free textbook stuff. So I haven't had time to do that, but tomorrow is my plan. So tomorrow morning, I'm hoping to do a lot of grading, and hopefully I'll have your projects graded. I haven't even started yet, but tomorrow I'll do either all of it or some of it. I teach stats at 3:30, so we'll see if I can finish by 3:30 is the plan. So let you know that the projects will be graded within the definitely by Wednesday, but probably by tomorrow at 3:30 is the hope. So just let you know, sorry if you haven't heard from me yet, but yeah, sometimes life gets in the way of the teaching. So that is the plan. Are there any questions about anything about the class or anything you've been doing or anything about statistics? Any questions? So I'm always happy to answer questions. Often that's when it gets quiet. All right, if there aren't any questions, I'm going to let you know I'm going to do all of this using the common theme of an example. And to me, it's the most important regression analysis example that has ever happened in my town. And I don't know how many of you live in Tahoe, but you will agree with it, that it's the most important. Okay, it's not just my opinion or something, but it's definitely what everyone cares about here, which isn't true if you live far away. Then you won't care about it that much, but hopefully you'll understand it. So I'm going to go through that. So I want to talk about first scatter plots. And we've dealt with scatter plots already, just a picture of them, and we can do it again. And I thought maybe we do something fun with you guys again for the scatter plot, just kind of the first idea of scatter plot. I'm going to do it point by point. And this is something I do require you to do. I want you to put in the chat box and see if there's anything interesting that you want to find out about each other that involves possible regression analysis, which means that two quantitative variables. So in other words, two survey questions where the answer is a number at which you think there might be a relationship, maybe a possibly somewhat linear relationship between the two. So any thoughts that you want to ask each other? Anything of interest where you want to find out, if I know about this particular quantitative number about a person, then that'll give me some idea about this other one. Anything you'd be interested? I always like to let you talk. First one to pop it in the chat box or to say it, I'll go for, as long as they're quantitative things. Okay, how many classes do you have left for your degree? Two things, remember. So you want to use one to predict another. So how many classes is definitely quantitative?
How old are you?
Okay, so how old are you? And I would say that, would you want to predict how many classes they have left based on their age, or do you want to predict their age based on how many classes they have left?
How many classes they have left based on their age?
Okay.
Agreed.
Okay, so the first question is, how old are you? And also let's be a little more specific about the degree. Do you mean your current degree you're working on now, or do you mean your overall goal, the last degree you're going to get? Because those are different for some people, at least. What would you like to hear?
Degree.
Huh?
Current degree?
Okay, so the current degree. The only problem with that is some of you are going to say 0 because you're done at the end of the term, but we'll see how it goes. I hope you don't all say 0 because then it gets boring. The rule, by the way, is you do not have to tell the truth. Okay? My guess is, and I'm not going to like give you, I'm not going to say, well, you know, Sarah said this and that. I'm not going to say who said what. I'm just going to put numbers in. Okay? The first thing I want to do is I want to go to the calculator, because we're going to do this by calculator. And we're almost there. Which number do you think we're going to be using today?
24.
24, and that's the only number today. Today is all about regression analysis. And as you can see, we're almost done. I bet you can guess what we're going to do next week. So I'm going to hit number 24, regression analysis. And then we're going to plot points 1 point at a time. And the rule is you have to put your answers in the chat box. Again, you don't have to tell the truth. But if you're going to lie, be reasonable. Don't say you're 950 years old. Okay, if you're going to lie. But hopefully you tell the truth. Again, I'm not going to say who's who to the world. So put in the chat box. The first number should be your age, right? Because you want to use the age to guess on how many classes are left, right? So your first number should be your age, and then your second number that you type in should be how many classes you have left. Yeah, it's a number, comma, a number. Otherwise, it's going to be really hard for me to get these numbers in. Yeah, so it's a number, comma, a number. And then I'm going to start putting things in. Okay, so let's just type them in. And again, I created this calculator, and there's a couple ways to use a calculator. One way is just 1 point at a time, which I think I'm going to do it that way. So we have 36, 36, comma, 6. And I hit plot points. And there we go. It plotted it. And then the next one was 40, 0. So you're done in 3 weeks, I guess. Plot points. And there's the next one. And then the third one, 4912. And I'm going to hit plot points. And then 38.1. And I'm going to hit plot points. And then we have 39.22. Wow, that's a lot more glasses. You will not be done at the end of this year, that's for sure. I hit plot points. Okay, and that's everyone. Okay. So what this just did is it creates a scatter plot. So you'll notice that the x-axis or the horizontal axis represents the age of the person, and the vertical axis represents the number of classes that the person has left to take. And all a scatter plot is plotting the points that represent those coordinates. Any questions on the scatter plot? Okay, notice, by the way, this draws something else besides that, and it's good to look at it. What else does it draw? What else do you see drawn besides the scatter plot?
A line with a slope.
Right, a line. Okay, a line. Well, all lines have a slope unless it's vertical, but
Right.
So we see a line. Okay, and what that line is that is sometimes called linear regression line. Also, sometimes you'll hear it as the line of best fit. Have you heard of those words before? So what that is, it is a line which is kind of the best approximation or the best estimate helper for this data. You look at the data. Is the line a good fit? What do you think?
No.
No. These points, if I didn't have this line drawn and I told you to draw what you thought was the best fitting line for these points, my guess is most of you draw something different. Okay? Because these points don't look anywhere near the line. Does that make sense? Okay, yeah, there's 2 points that are close to it, but the others aren't. Okay, in fact, you can even maybe draw a slope line that goes down like that. That might look even better. So these points are all over the place. You see that? All right. When the points are all over the place, then we're going to say that there isn't much of a correlation. Whereas if the points are really close to the line, then we're going to say, yes, there is a correlation, a strong correlation. And in fact, if the line has a positive slope, we say that there's a positive correlation. If the line has a negative slope, we say that there's a negative correlation. So if we look at this picture, do you think there's a positive or a negative correlation between these two, even though it's not much of a correlation, but is it positive or negative what it is? Hopefully you can look at this and tell me. Yeah, there's a positive correlation because this line has a positive slope. Okay, but we can also say that it's a very weak correlation. It's weak positive. Any questions on that? Okay, so from the scatter plot, you can do that. You can look at this. You could even estimate the slope. How do you estimate the slope of a line? Who remembers from just basic algebra?
1/2 base times height.
That's a good guess, but that's actually the area of a rectangle. I mean, triangle. So you're remembering a formula for something else. That's a formula for the area of a triangle. But for the slope of a line, something that you all have heard of, I promise. If no one remembers, I'll say it and you'll say, oh, of course. Remember?
Is it y equals ax plus b?
Okay, that's the equation of a line. Okay. And by the way, for statistics, you usually do a plus bx, just let you know that. But that's not the slope of the line. That's the equation line. How do you find the slope of a line? Remember?
Is it rise over run?
There we go. Rise over run. I figure somebody would remember. So rise over run is the slope of the line. It's very important. So in particular, for example, these 2 points right here, they're kind of right on the line, just about. So I'm going to just use those. This first one was our lowest age, our youngest person, I guess I could say. That's the 36.6. And the second one happens to be the oldest person. So 36.6 and 49.12. So the rise is how much the y coordinate has changed. And that is the difference in the number of classes. So that went from 6 to 12. So 12 minus 6 is the rise, and 12 minus 6 is 6. The run is the difference in ages, right? The x difference. And that is going to be 49 minus 36, which is 13. So the rise or run is 6/13, which is a little less than a half. So we can look at this and just visually say that the slope of the line is a little less than a half. Okay, do you think the y-intercept, so by the way, the slope of the line is a rise or a run, and the rise again was the change in the number of classes the person has to take, and the run is the change in age. So if it's a little less than a half, that means for every additional year somebody is in age, they're going to have approximately a half more courses to take. Okay, or a prediction of that. Now, this prediction is awful because it's nowhere near the line. That's just a note. What about the y-intercept? Not visually, but what does the y-intercept mean? Do you remember? In algebra. What the y-intercept means. So slope is rise or run. What's the y-intercept? Do you remember? Maybe been a while since you had algebra and basic algebra, very basic. Remember the y-intercept?
Where it crosses 0?
Okay, I loved your first few words. Your last wasn't so good, but where it crosses, something in the message. Yeah, where it crosses the y-axis. Okay, where it crosses the y-axis. Okay, but we can also say that it's 0, but not where it crosses 0, but what we can say is when x is 0, then the y-intercept is the y value when x is 0. Does that make sense? In our case, x, remember, was age. So the y-intercept is going to be how many courses a person has left to take for their major and for their degree that they're working on when they're 0 years old. Do you think this has very much useful meaning?
No.
No. Come on, when your mother gave birth to you, you were not thinking about how many classes you have left to take in your major, in your degree. Okay, you were just thinking about milk, maybe, or something like that. Okay, none of us remember what we're thinking about, but we weren't thinking about how many classes left to finish our degree. So this is one of those where the y-intercept is pretty meaningless. Does that make sense? So I'll let you know, sometimes the y-intercept has real significant meaning and sometimes it doesn't. This is an example where the y-intercept is not meaningful at all. Okay, it's an important number, but you can't really relate it to our survey. Any questions on that? Okay, now I'm going to scroll down a bit and it's going to show the important numbers. Again, we're seeing numbers right now. And then I'll give you a better example, where the numbers actually have more meaning and stuff later. So first thing is R. So in this example, oops, let's not do what I just did. There we go. R is about 0.2, just to one decimal place. It's probably good enough. So 0.2 is a small number. So I'm going to let you know that R, which is a correlation, is always between -1 and 1. So if it is closer to 0, which 0.2 is definitely closer to 0 than it is to 1, then there's not much of a correlation, which we can see just from looking at this regression line, is that the line is not a good predictor at all. Okay, so typically, once you get your R, and if you see that it has something like 0.2 as the correlation, you give up and you say regression analysis is worthless. Any questions on that? Okay, here our equation was -9.2 plus 0.4x. Okay, which is good because the slope is about what we thought it was going to be, a little less than a half, right? So slope really is a little less than a half. The y-intercept is -9.2. Another reason why it has no meaning. That means that when you were born, you had your best prediction for the number of classes you had left from your major was -9.2 classes, which is just silly. Okay, so it doesn't mean it's wrong. It just means it's not very useful. But it is part of the line. Any questions on kind of reading this stuff before I get into better examples where we actually get a good correlation?
Yeah, I have an example. Can you go, or not an example, a question. Can you go over like what the R value represents again?
So the R value represents, if we look at the line and the dots, is that line a good estimate for our data? And we can see the points are all over the place, right? Do you see the points are all over the place?
Yes.
So our line is a terrible estimate for the data, right? Do you agree?
Oh yeah, yeah, absolutely.
So if it's a terrible estimate, that means R is going to be close to 0. Whereas if it's a good estimate, R is going to be close to 1 or -1. Does that
Okay,
help?
awesome. Yeah,
Yeah.
thank you.
So that's really important. And typically, and there's no exact number people use. Sometimes they'll say it's a strong correlation if R is greater than 0.8, because that's close to 1. Do you see that? Or less than -0.8 on either side.
Yeah.
And you'll often say it's a moderate correlation between 0.6 and 0.8. So sometimes you'll hear that. And point 2, which is what we had, is very weak. Okay, in terms of how you understand the numbers. I'm going to get into the R squared a little later because that's actually harder. And I want to get that in detail where it's actually useful. This one's not that useful. It's only 0.06, which is really close to 0. And I'll get into the hypothesis test later too. We'll do a hypothesis test for something more important. I mean, this is a fun little example. But one of the things, by the way, and there's something to note, how big was our sample size? Yeah, it was 5. Do you think 5 is a big enough sample size? Hopefully you've been in this class long enough to tell me.
No.
No.
5 is a terrible sample size, okay? You would never, ever use regression analysis with a sample size of 5 and try and say you have anything. Does that make sense? So there's all kinds of problems with this example. And one is the sample size is just way too small. So again, sample size of 5, don't go there. And that hopefully at this point in the class, you got that down. That 5 is never okay. All right, so now let me get, are any of you from Tahoe? Do you have any Tahoe people other than myself? No one from Tahoe? I don't think I've ever had that in a class where I had at least 5 of you. 5 out of 5 are from not Tahoe. That is a rare thing, because this is, hopefully you know, this class is taught officially at Lake Tahoe Community College. That doesn't mean you have to be from Tahoe, but usually I get a few people. All right, have any of you been to Tahoe or like Tahoe a lot?
Yeah.
Okay, what's the most important thing we care about when it comes to collecting data in Tahoe?
The lake.
A lake. And what about the lake?
It's blue.
It's blue. Exactly. It's blue. And what that really is, and I'm not going to get into chemistry, by the way, but there's some chemistry reasons why it's blue. And in particular, it means that you can see really deep. Okay, that's what's amazing about Tahoe. If you've never been to Tahoe, by the way, I strongly recommend you come to Tahoe because it is a beautiful place. And those who have been here, I think you'll agree, even though you don't live here. I'm biased because I do live here, but I do think it is absolutely beautiful. So it is blue. So the most important thing in our town is making sure that our lake stays clear, stays blue, and doesn't get all murky. Does that make sense? Okay, and it's almost, there's not even questionable. That is the biggie. Okay, so I'm not sure if you know, but the group that is responsible for collecting the data and analyzing it, any guesses? What, who does it? It's not Lake Tahoe Community College, by the way.
The citizens.
Good try. Keep Tahoe blue. Good idea. Nope. No. All right. I'm going to tell you because you probably won't guess. UC Davis. So UC Davis has their research center in Tahoe. It's called the UC Davis Tahoe Research Center, Lake Tahoe Research Center. And they're the ones that do it. And it turns out, let me give you some, this is like, there are some things that make me happy. And this is one of them, given that I teach statistics. I was talking to the guy who's in charge. He gave some talk or something. And we chatted a bit. I told him I bring this into my class. And I asked him, you know, so when you collect the data, because they analyze the clarity every year, right? So is there just one day in the year that they do that? Do you think that'd be a good idea? Just look one day a year. Now, how, so this is, you're going to smile when I tell you what happened. So I asked him, how many days a year do you look at the clarity? Do you make sure of it? And do you know what he told me? He said, at least 31. And I'm like, yes. So what they do is they collect the average of 31 days in a year, each year. They've been doing it since the late 1960s. And they collect the data. And because they do more, at least 31, then they know that the distribution is normal. Isn't that wonderful? And that's important because you want that for regression analysis. So that means that you take an average and talking about sampling distribution. Central limit theorem tells you that you have an approximately normal distribution. At this point, you should all know that, right? So let me tell you another kind of fun little piece of history. This was in the year 2000. So they collected up to 1999. And the most important person in all of America came to Tahoe. Anyone know who that was?
The president?
Yep, President of the United States. Anyone who that was? See if you know your history. No one knows your history. I saw your ages. You're not that young. Some of you. Okay. President Clinton. And my statistics student was there serving him his dinner. And what it was the UC Davis Research Center was giving President Clinton an explanation of what's going on in our lake. And let me show you what they showed him in the year 2000, and we're going to talk about it. So I'm going to give you the picture. I think I need to make it a little smaller because you probably can't see the whole thing. So let me make it a little smaller. Need a little bit smaller. Okay, so there it is. So this was the picture that they gave. And, pretty little picture. They showed it to the president of the United States, and there were some other important people there too, but no one as important as the president. And the good news, and not like every president we've had in our lifetimes, President Clinton actually understood science and statistics. That's a good thing. I would love for like a statistics class to be a requirement to be president of the United States. Because then they actually would understand data and science and stuff like that. But we can't do that, unfortunately, because of the Constitution. But he did, and he looked at this and understood it. Okay, so here is the data. And by the way, so 70, for example, means the year 1970. Okay, and 25 is 25 meters. And what they do is they bring a siki dish. And what that is literally what it sounds like. It's just a little white plate. And they lower it down from a boat till they can't see it. And then they measure how far it went down. And they do that every year for 31 times, average it out, and then create this scatter plot. Any questions on this? So this is a scatter plot of the depth of clarity of Lake Tahoe over time up until Clinton actually was there. What do you notice? Is this like the last scatter plot we saw when we looked at age versus number of classes you have left in your degree?
No,
Now, how is this different?
it's closer to the line.
Yeah, this is definitely closer to the line. Okay, you can definitely see a trend. There is no question about a trend. Ready for a trick question?
Yes.
Is the correlation positive or negative?
Negative.
Okay. Did you hear what the word I said before trick? Before question? The trick question. And this is one of these weird things. And sorry, I gave you a trick question example. But look at the y-axis here. 15 is up high, 20 and 35 is down low. So you have to turn this upside down. So now maybe you can change your mind. Is this positively or negatively sloped given the fact that the y-axis is upside down? Now it should be easy now that I told you. So what is it? Is it going to be a positive or a negative correlation given that you have to look at everything upside down?
Negative.
It's negative, because notice that in the early years, the depth of clarity looked like around 30-ish, right? Whereas in the later years, the depth of clarity was just a bit above 20. So clarity definitely changed. Do you see that? Okay, and it changed for the worse, which means that it got murkier. Any questions on this? So just from visualizing this, we can see that there is a negative correlation. It's not perfect. Okay. If the correlation is exactly -1, any guess on what that means about the points?
Then all of the points are exactly on the line.
Yeah, exactly. With a negative slope. And if the correlation is exactly +1, that means the points are all on a line with positive slope. Let me give you an example of a correlation with +1, because those are easy to think about. Let's suppose I asked you 2 questions. The first question is, how tall are you in inches? The second question was, how tall are you in centimeters? And we're going to assume you have a calculator so you know how to do the translation. Then that would have a correlation of 1, because there is a mathematical linear equation that tells you if you know how many inches you are, you know exactly how many centimeters you are. Does that make sense? So all the points would be exactly on the line that goes through centimeters, inches. Or if I asked you another example with a positive 1 correlation, would be, what is the temperature in Fahrenheit? Okay. Or let's go, what is the temperature in Celsius? And what is the temperature in Fahrenheit? And that's going to be exactly on the line, y = 9/5 x + 32. Do you remember that? I don't know if you remember that equation, but that was an equation for centigrade Fahrenheit. So if it happens to be exactly on the line, you get exactly r = 1 or exactly r = -1. Any questions on that? Okay. But this is not exact. So r is not going to be 1 or -1. Okay, it's going to be negative because remember it says upside down, it goes negative. So we can definitely see we have a strong correlation. What's your guess on what the correlation might be? What might be r? Any guesses? What number might it be? Based on what I just said.
-0.8.
Yeah, maybe -0.8 sounds good. Okay, somewhere around -0.8. Okay, so notice, by the way, you can definitely say as the years have gone up, clarity's gone down. But there's sometimes over here, like between 1983 and 1987, notice the clarity got better as the years went on. Do you see that? So that's why it's -0.8 instead of -0.1. Okay, if it was -0.1, you'd never have this other slope, this upward slope, even though it looks downward, but it's upward. Okay, so it does go up and down, but it tends to go up as the year, tends to go down as the year goes up because you have to look upside down. Any questions on that? Okay, so the next thing is, let us actually get the numbers. And what I did in the 20 minutes before class, and this you have to, I'm not perfect, by the way, so don't 100% trust me, but I eyeballed all the data values. This took a long time, actually. And I wrote them out. So here were the years. Those are easy because those are off by 1 each year because they do it every year. And here is the depth of clarity, separated by commas. And what I'm going to do is going to copy. I'm going to go into the calculator and hit new plot so we can start over again. I'm going to go paste and let the year be the x. You always have to decide which is independent, which is dependent. So we're trying to guess clarity based on year. You're not trying to guess year based on clarity. Okay, then we're going to go back and we're going to copy the clarity numbers. Into the y. Okay, you could do these 1 point at a time, but that would take all day. So I wanted to save you the pain, and I figured I'd just write them all out. It took me a long time. And then I hit plot points. And take a look. Notice now it's not a trick question anymore. Hopefully it's clear that we have a negative slope. Okay, so I'm not the UC Davis people trying to make it pretty with a boat. Now I'm talking reality math-wise. And that is the scatter plot. And there's our line. And now we can see the line looks like a pretty good fit, doesn't it? So now we can look at, let's see how good our guess was for the R. Not bad. Negative 0.847 or so. Okay, in fact, to one decimal place, negative 0.8. So we can say that there's a pretty strong correlation. So let's write that out. Measurement should be in fathoms. Yeah, I'm not into that. I'm into science. So there's a pretty strong correlation between the year and the depth of clarity of Lake Tahoe. Any questions on this example so far? Okay, so I want to note something since I put it up here and I can read it. So again, R is a correlation. It's always between -1 and 1. The sign of R is the same as the sign of the slope. Maybe I'll make this bigger so you can read it a little better. If R is close to -1, then the points are all close to all being on a negatively sloped line. If R is close to +1, then the points are all close to all being on a positively sloped line. So in particular, if the slope is positive, R is positive. The slope is negative, R is negative. Okay. If R is close to 0, there's no line that fits the points well. Okay. Often, the scatter plot looks like the night sky. Okay. Maybe some of you are live in a city and you never actually see stars. But if you live in Tahoe or you live in a place where you can actually see the stars in the night sky when everything is dark, okay, or maybe you live in Seattle and it's always cloudy and you can never see anything. But in Tahoe, our night sky is beautiful. But if you look at the correlation, say between east-west and the north-south, basically you look at the position of the stars as scatter plots, then R is basically 0, right? There's no linear correlation for stars. So that's why I like to use that because most people know what the night sky is. Sorry if you're from Seattle and you have no idea, or New York City. But if you live in a place you can see the night sky, you understand. Okay, then that be a correlation that looks like very close to 0. The other time you'll see a correlation that's close to 0 is if the points lie in a parabola, for example, then they don't fit a line at all. They go down, then up, right? Or up, then down. So sometimes you'll see them on a parabola and that's still an R close to 0. But more common is when they're just literally all over the place with no trend whatsoever. And if there's no trend whatsoever, then R is going to be close to 0, which we saw there was very little trend when we were looking at the age versus the number of classes you have left to take for your degree. Any questions on the correlation? Okay, now comes R squared. Okay. And by the way, let you know when I took stats, it was not elementary stats, it was mathematical stats. My professor gave an entire 2-hour lecture on looking at the difference between R and R squared. So it's a lot deeper than just square the number. Okay, in terms of mathematically, you can just square the number. But to truly understand what it means, it's very deep. And I'm going to give you kind of a simplified version of it. Okay. And that, do I have that here? Where is that? Did it get lost somewhere? Yep. Okay, so let me retype it. I think it got erased when I put the picture in. So R squared first thing, very basic, is the square of R. Okay, which doesn't really help you understand it at all. So the first thing is best to make it a percent instead of a decimal. Okay, so let's look again. Our R squared is about 0.72. So our R squared is about 72%. Any questions on that? And here's how we interpret it. So the variation, and let me write or standard deviation because that's what we've learned in our class. In the y variable is considered large. So for example, in our case, if we look at the variation of the y variable, notice it goes from about, the lowest was around 20 and the highest looks like around 32, right? That's a pretty big variation in depth of clarity. Do you agree? So going from 20 to 32, it's all over the place. So it has a pretty high standard deviation. But if you just look at y values that all have x values that are almost the same, then the variation right, which means standard deviation, is reduced by R squared percent. All right, so that's pretty it's pretty vague, right? It's pretty abstract. So now let's talk about it. Let's talk about it with Lake Tahoe. So what we can say is that over the past, so over the let's see, 1968 to 2000 is 32 years. Over the 32 years, there has been a large variation in the depth of clarity. Of Lake Tahoe. So again, you look at the picture and it's pretty different. Again, it goes from 20 to 32 meters that you can see down. It's a huge difference in clarity. Okay, and it's all over the place. Okay, it's not like all of them are near 20 and then there was one over here. There's some that are low, some that are high, some are in the middle. Do you see that? Some are a quarter of the way there, some are a third of the way there. They're all over the place. But if instead we just look at, say, these 3 years, notice they're not all over the place. They're almost the same number of meters. You see that? Or if you look at these 3 years, or if you look at these few years, or if you look at these few years. So if you only look at a few years at a time, where the years are all kind of clustered together, sometimes you call that a cohort, then there's not a lot of variation. They tend to stay about the same number of meters of clarity, of depth of clarity. Do you see that? So now let's continue on. But if we only look at a few years that are consecutive, the depth of clarity or the variation in the depth of clarity is reduced by an average of, and now remember R squared was about 0.72 or 72%. Okay. Sometimes you'll say that 72% of the variation in depth of clarity can be explained by the year. While 28% is due to other factors. What other factors might there be that will change the depth of clarity in Lake Tahoe? This is not a math question, it's a science question. Anyone know?
Water runoff.
Yeah, water runoff, and in particular, how much snow we got. Because if you have a lot of snow, you get a lot of water runoff, right? By the way, if you've never been to Tahoe, I will tell you, we're a place that has a lot of snow in the wintertime. So if you don't know about Tahoe, that's what we've got. So in big snow years, our depth of clarity goes really down. Okay, whereas in drought years, our clarity is pretty good. So any guess on 2021, how our clarity is going to be? Think it's going to be better or worse than last year or the last few years?
Better.
Should be better because we're in a drought this year. So again, if you're not live anywhere near here, then, you know, if you're out in, I don't know, China or something, then you might not know that, but we're in a drought. So we could expect it to be better, but probably not as good as it was, you know, in the year 1968, because things have gotten worse every year. Do you see that? Any questions about looking at R squared? Okay, so now that we understand R and we understand R squared, we understand the scatter plot. Now let's take a look at the line. And again, if we go back to the picture, there's definitely a line. Any questions on the line? Okay, I'm not going to get into the intense mathematics, but this line minimizes the squared vertical distances from the points to the line. So if you don't know what I'm talking about, don't worry about it. Okay. And if you really love math, there's some really cool matrix algebra involved, but we don't do that in this class, but it is kind of cool. So right now, I just want you to be able to look at it and say, hey, the R squared, I would say R squared is going to be pretty big, and R is going to be a high negative number. Okay. High means close to -1. Okay. So that you should know. You should know the slope of this line is negative because it definitely goes down. And then if we look at the equation, here's the equation. Often they put a hat there, but honestly, to program the hat is such a pain in the rear that I didn't make it happen. You don't know how much work that would be. It would be days of work just to make that hat happen. So that usually has a little Y hat on it, which means estimating Y instead of knowing Y. So I want to mention that for this program. So Y hat is equal to, let's just say 45.6 minus 0.247x. I'm going to go 3 decimals. Any questions on that? Okay, the good news is that it's not that hard to do a Y hat with Google. So Google likes hats. I just go to equation, I go Y, and then I highlight the Y, and then I make a hat happen. I think it's there. There it is. And there's my Y hat. Okay, still hard to see, but at least it's got a hat. And then it was what, 45.6, if I remember right, minus, and then it was negative minus 0.247. X. And I want to make that bigger because it's important, very important. All right, so let's see, just a note, predict. What is the best prediction? For the Lake Clarity this year. And let me remind you, that was 2021. So, and we're doing, that would be in that case, 121 in terms of the x-axis, because remember the x-axis was years since 1900. Any questions on the question? And the hint is, this is very easy. How do you think we might make our best prediction for Lake Clarity this year based on our regression analysis? Hint is it's easy. Everything is there for us. Put that in, that might help.
Multiply 121 by 0.247.
Keep going. Part of it. Here's a hint. That's a hint.
Just work the equation.
Yeah, we just plug in. That's all we have to do. Plug in 121. Okay. And I could do that with basic Google calculator. So I can just say 45.6 minus 0.247 times 121. And we get about 15.7. So the answer is 15.7, right? Yeah, 15.7. So the best prediction for the Lake Clarity in this year is 15.47 meters, 15.7 meters. Okay, which is pretty horrible. Do you agree?
Yes.
Okay. I mean, given that in 1968, it was over 30 meters. So that means that clarity from then to now, our prediction is a reduction by 50% loss in clarity. Do you see that? So we lose 50% of our clarity. Any questions on understanding what this says? All right, just another note. Now it's time to talk politics. And that is, what happened is Clinton was, sitting at the restaurant and they were showing their, their boards. They had it on big whiteboards, I guess. And Clinton said, this isn't okay. So historically, what happened is in the year 2020, Clinton talked to Congress and got Congress to pass a law to fund the improvement of the clarity of Lake Tahoe. Because having a 15-meter or 16-meter clarity is not acceptable for Lake Tahoe. It would just be murky and gross, and we don't want that with our environment. So literally many millions, I think over $100 million was spent from then to now on helping Lake Clarity. So I want to mention that regression analysis works if things keep going as they have been going. But since they passed the law, then regression analysis is a terrible predictor because they're changing things. Do you see that? So do you want to see what it looks like now? So here's the current, with all the current data. We don't know 2021 yet because our year is not over yet. And what do you notice that happened after the year 2000? From here to here, what happened to Lake Clarity?
It's gotten better.
It's
For the
gotten
most part.
better, and at least it hasn't gotten worse. It didn't keep getting worse and worse and worse and worse until there was like nothing left. Do you see that? So I love this example because it's where regression analysis made a big difference. So because of regression analysis, they were able to make that prediction and then convince the government of the United States to do something about it. And that, to me, that's what statistics is all about. Okay, yeah, it's nice to say, oh, we got regression analysis and there's an equation. But if you're not going to do anything with the equation, what's the point? And this is an example where they did something about it. They did it right here. And then all of a sudden, everything changed. All the bad stuff stopped. And they were able to keep it, level. Okay, no, it still went up and down and up and down. This time right here, big drought. Clarity got better. Do you see that? And then over here, lots of snow. Clarity got worse. Okay, so then all of a sudden it's not about the fact that we're just progressing in years. Now it's about just weather. And that's what we're hoping for, that only weather is affecting lake clarity and not the fact that there's people destroying the lake. Okay, there's still some issues. We're worried about global warming, but that's a whole different thing, and I'm not going to get into that. It's a little too complicated, and that might hurt lake clarity also for different reasons. Okay, but that's statistics also. Any questions on this example so far? Okay, let's take a look again at this line. Where was it? There it is. And let's look at the slope. Okay, the slope is, I'm going to go negative 0.2. It's just easier to say. So the slope is equal to negative 0.2 about. And remember, that's the rise or run. And rise is the change in y over run is a change in x. Y is the year. X is the year and Y is the clarity. So it's a change in lake clarity over the change in year. And I can rewrite this, and this may seem stupid, but it's worth it. 0.2 divided by 1. Do you agree that negative 0.2 is the same as negative 0.2 divided by 1? I hope you all know that basic math. Okay, the reason I did that is so I can write it as a rise or a run. So the over 1 means 1 year change. So now we can use this and we can interpret the slope in the context of the study. So in particular, we can say that for every year that passes, our best prediction is that the lake clarity decreases, negatives or decrease, by an average of 0.2 meters. Any questions? Any questions on interpreting the slope? Okay, so it's every 1 unit that y changes, that x changes, the best prediction is that y will change on average of whatever the slope is. In this case, we have a negative slope, so the change is a decrease. Have I lost anyone? Okay, even more important is, can you do this kind of sentence given a regression line? You know, not about lake clarity and year or anything, but whatever it might be. Right? Could be, I don't know, month and COVID or something, COVID positives or something. And right now we're definitely negative, by the way. We have a negative slope, which is good. Fewer COVID cases. Any questions so far? How about the y-intercept? Do you think it's a worthy predictor or not? So by the way, the y-intercept is 45.6 ish. Okay, well, one thing is when x is 0, that's the year 1900. And if we look at the picture, then the year 1900 is nowhere near any of the data values, right? It wouldn't even be on my computer screen. It's so far away. If you're nowhere near the data values, then you don't want to use the regression line to predict it. So you only use the regression line to predict events that are not that far from the data. So you don't want to go far, you know, back to the year 1900 when we only have from 65 to 2000. Okay. 2020 is not quite as bad because that, you know, 65 to 2000 is a spread of, you know, or 68 to 2000 was a spread of 32. So that's just going another 21 years, which is less than the spread. Do you see that? But the year 1900 is way, way far. So since the year 1900 is far from the data, the y-intercept is not a good prediction. Predictor, I think, is a better word. Okay. If we decided it was for some reason, then we would say that our best estimate for the year 2000 is lake clarity was 45.6 meters. Okay, that's how we would use it. Any questions at all on, or the year, sorry, 1900, lake clarity was 45.6 meters. Any questions on the idea of the y-intercept? Any questions? Okay, I'm trying to do like one example in full, because I think that's better than just rushing through a lot of examples over and over again. But they're all kind of similar. Okay, one can change is that the y-intercept sometimes does have meaning. Okay, the two examples we've looked at, there's no meaning to them because being 0 years old and looking at how many college classes you have left is silly. Okay, any questions on any of this so far? Okay, I want to mention something very important, and that is language. We have things like the best prediction, Okay. We have things like another best prediction. Sometimes you'll see there's a tendency for, or there's a trend of. Okay, those are good words to use with regression analysis. Any questions on that so far? So now bad words to use with regression analysis. Never use cause. Let's make this bigger. So never use cause when you're talking regression analysis. Okay, so for example, if you're looking at how many gray hairs a person has and how old they are, let's let X be the number of gray hairs and Y be how old they are. Do you think there's going to be a correlation? What do you think?
Possible.
There should be, right? If you see someone with a lot of gray hair, are you going to guess that they're not 15 years old?
Yes.
Right? If you see someone with no gray hair, then they're, especially if they don't dye their hair, they're probably not 85 years old. Does that make sense? Okay, unless they're a male. You know why? Men at 85 often have no hair, so they have no gray hair because they're bald.
Mhm.
If I ever get there, it could be me. So we'll see. So far, I have hair. Okay, so there's definitely a correlation between number of gray hairs and your age. So does that mean that if you give someone more gray hair, they're going to get, that means you're going to make them older?
No.
No, if you dye someone's hair gray, you're not going to make them older. Do you see that? Or if you take away their gray hair, if you cut all their hair off, you can make them younger?
No.
No. So this thing, you don't make something happen. There's no cause. You can't use those words. Okay, it doesn't mean there isn't a cause. It means you can't get it from regression analysis. It doesn't work. And because, by the way, if you get rid of the BE, it still says cause. So it's another dangerous word. I don't know if you ever thought about it, but because is a cause word. Okay. If then it will is another one you shouldn't say. Okay. So if you, dye someone's hair gray, then they'll get that they will get much older while you're dyeing it. Okay, which is just wrong. Okay, you can't say that. Okay. Even if you know there's a cause, if all you have is the regression analysis, you still can't use those words. Okay. So for example, originally, when they were first looking at smoking and average age of death, they looked at statistics and they found out people who smoked a lot tended to die younger. So if you look at the regression line, it was very clear. Okay, it wasn't an R equals 1. Oh, sorry, R equals -1 for number of cigarettes versus how long you live. But it was a high negative correlation. More cigarettes, less life. So from just the data, could they say that smoking cigarettes caused early death? What do you think? Okay, the answer is no. Okay, you can't. But so here's what you do. And this is where coordination and collaboration come in. So what you usually do is you collect the data, you have a hypothesis, you look at the data, you find the correlation. Then what you do is you go, all right, doctors and biologists, we have a correlation, see if you can find anything. And then what they do is then they do medicine. And they look at what's happening chemically with cigarettes, nicotine, and lungs and cancer and that kind of stuff. So the statistics helps them see if there's a cause. It gives them that thought that there might be a cause, but it doesn't say there is one. The science is what shows the cause. Do you see the difference? So you can get a cause, but not from statistics. You get it from the science. Any questions on that? Okay, the last thing to talk about is hypothesis testing. So we can say, is there a correlation? Is there a correlation between the two variables? If there is no correlation, then you basically don't do linear regression analysis. You just don't go there. You don't use the regression line to predict anything. You don't talk about interpreting R squared. You just give up. You say regression analysis is not the way to go. Sometimes you get more advanced and you take a logarithm of something, but I can't talk about that because this is elementary stats. But I'll let you know if you take another class in stats, then you'll talk about other things you can do besides linear regression. Okay, whether that's quadratic regression or logarithmic or exponential regression. But if you don't have a correlation, you can't do linear regression. So we have the hypothesis test, H naught rho equals 0. And in our class, we're just going to do H naught rho not equals 0. You can talk about a positive correlation or negative correlation. And then you're going to have rho is greater than 0 for positive correlation, rho less than 0 for negative. But I will let you know on the final exam, it'll be, is there a correlation? It's not going to be positive or negative. You're just going to, for a hypothesis test. Rho, again, is the letter that we use for correlation because it is the Greek letter for R. So it's a population correlation, which is different than the sample correlation, which is what R is. Any questions so far? Okay, so then once you have your H naught and H1 written, and by the way, this is not chapter 11. How many words do you see in this H naught and H1?
None.
None. We're back to none again. Okay, chapter 11 was all words. Chapter 9, 10, and 12 are all symbols. So get that down. Okay, that's a requirement. I will take off points if you write down words for H naught and H1 for a test question. Got it? All right, so then what you do, and hopefully you're used to, what's the next step after writing down H naught and H1 and you have the data?
Go to the calculator.
Go to the calculator. The calculator does it all for us. You can choose a less than or greater than, but the default is not equal to. For an exam, stay on the default. Just let you know that. It turns out, and this is just kind of cool mathematics, which I can't explain, that it's the same test statistic mathematics that we had for a hypothesis test for a mean or two means, and that is T, students' T distribution. The reason is way complex. I'm not going there. Got it? But I'll let you know it's the T distribution again. Same distribution we had a while back. The p-value. Is the p-value about 9.7?
No,
No. P-value could never be 9.7. How come?
it's bigger than 1.
Yeah, p-value is a probability. You can't have a probability of 9.7. What's the p-value here?
You have to move the decimal 10 places because of the E.
Exactly. It's easier to say than actually saying all the zeros. But I'm going to say them anyway. It's 0.00000000967. Okay. P-value is basically 0. So let me write that down. So P value is equal to 0.67, I think it was. Let me double check. Yep, 967. All right, now hopefully you all know what to do when you get a p-value that looks like this. And what do we do?
Reject H naught.
Yeah, so we reject H naught. So there is, I'm going to write very strong, statistically significant. Basically, I can brag because it's such a small p-value. Evidence to conclude that there is a correlation between the year and the depth of clarity. Any questions on the p-value, interpreting the p-value, H naught, H1? Any questions on any of that?
You just wrote out a sentence, but you said we can't, we only have to, we can only do symbols.
Okay, symbols, right. So see what's in red?
Uh-huh.
The hypotheses are symbols.
Oh, okay.
The conclusion is always a sentence. And it
Okay.
always starts, I put very strong because it's so small, you might as well brag, right? But it always starts, there is statistically, and then it's either significant or insignificant. You remember that?
Uh-huh.
So we've been doing that for every chapter since chapter, 9, I guess. Yeah,
Okay,
so
so what are the sentences that people are writing?
what's that?
So what are the sentences on the exam that you took points off of for?
Oh, so if I ask you write down the null hypothesis
Uh-huh.
and you write H naught colon, and then you say there's no correlation,
Oh, okay.
that would be that would be wrong. You need to say rho equals 0.
Okay.
So here's the good news, and you can put this in your note card. I always say that, and then there's always some people that don't. Is that whenever you're doing a hypothesis test for chapter 12, it's exactly this. Exactly what's in red. H naught and H1. It never changes. Got it? For this class. Okay.
Okay.
For the exam. So get the free points. You get a note card. You have to know that it's chapter 12, you know, that you're talking about regression analysis. But once you know that, H naught and H1 are exactly this, never change. Okay, you don't have to put them in red, you can put them in black if you want. But that's always the case. Okay, whereas chapter 11, remember H naught and H1 had words.
Okay.
And one of the words, for example, for goodness of fit, what was the word you had to use? Do you remember? You remember what word do you have to use when it's goodness fit test? That's a requirement for our class.
Distribution?
Yeah, distribution. Okay. Okay. So each type of hypothesis test has its own flavor. This one's always rho equals 0, rho not equals 0. It's the easiest of all of them because it never changes. Okay. We're not going to do left and right tailed. Okay. They can be done, but I'm not going to test on that. Okay. Your homework might have that, but that you can always, you know, redo a second try or whatever. Any questions at all on how this regression analysis works? Okay. Where else might you use it? What are other examples where you've seen regression analysis or you've seen correlation, at least? In your life?
We see it in reports and things all the time.
Yeah, I've seen lots of reports. Let me give you some examples that they've looked at the correlation between, for example, the amount of reading that parents do to their children when they're at young ages versus their GPA in high school later on. Do you think there's a correlation?
Yes.
Yeah, in fact, of all things, so if any of your parents, of all things that they've researched, that's number one. That has the highest correlation of anything. And that is how much the parents read versus how well kids do in school later in life. That's number one. So if there's anything you can take out of this class, that's one. read to your child because it makes all the difference. Okay. So that's an example where they found out there was a strong correlation between the two. Okay. All kinds of different things like, you know, the amount of exercise you get per day or maybe per week versus lifespan. Okay. You think they're correlated?
Yes.
Yeah. Does that mean that if you exercise, you will definitely live longer?
No.
No, doesn't mean that, but it's still a good idea to exercise because you have that tendency of living longer if you exercise. Does that make sense? So there's definitely, that would be one you do regression analysis on. Is that clear? Okay, and there's some things that aren't correlated at all. Okay, so for example, how about the high temperature in Lake Tahoe and the score on the New York Yankees baseball game? Do you think those are correlated?
No.
No, that's going to have an R of like very, very close to 0. Can't even tell you if it's negative or positive. It's going to be like 0.01 or something. Okay, because the temperature has nothing to do with how the Yankees do in baseball. Does that make sense? So there's a lot of things that have no correlation at all, but you can always look at it. Any questions on the idea of regression analysis? On R squared, on the equation of the regression line, the slope of the regression line, the y-intercept of the regression line, the hypothesis test for correlation. Those are the main things we've done. Any questions? Okay, if there's no questions, again, that we don't have a test to talk about and all that kind of stuff, so I don't think I have to go, you know, extra long. We're at an hour and a half, which is kind of on the low side, but not extra low. So let me stop the share. And
Secret
I-
word.
Oh, thanks. Thank you so much. I haven't stopped the recording yet, so I can go. Ah, man, you don't know, it takes me like, it's like an extra half an hour of work for me if I forget to do the secret word for you. So, because I have to re-edit the whole thing. Thank you for reminding me.
You're very welcome.
And the secret word is tends instead of causes. So as one goes up, the other tends to go up or tends to go down. Okay, not causes one goes up, causes the other goes down. So tends is the secret word for the day. Thank you so much for reminding me. You saved me a lot of time.
No problem.
Okay, and just let you know, next week will be the last webinar. So we only have one left. And then, of course, the final exam is in 2 weeks. So still a while. But you have, it won't be Monday in 2 weeks. It'll either be Sunday, Tuesday, or Wednesday is the way I have it set up. So I'm here if you have any questions. You don't have questions, you can say goodnight. That's fine too. But I'm always happy to answer questions. Questions, Michelle?
No, I was just going to type thank you. That was informative. I appreciate it.
Ah, okay. Well,
Have a
thank
good
you.
evening.
Yeah,
Bye.
yeah. Regression analysis is wonderful.
Thanks. Bye.
Bye. Hey, Braulio.
Hi Larry, how are you?
Good. How are you doing?
Um, I'm fine. I'm kind of currently working with some students from the other class
Ah, because there are projects to do tomorrow.
in projects due tomorrow. Yeah.
I was actually surprised that there was no correlation for their example. I don't know when you came in. I don't see exactly when.
Oh, I didn't show up until 7, a little after 7.
So I think we had already gone. We went through how old you are and how many classes you have left to take for your major.
No, I definitely would have answered that if I were here. I'm sorry about
No,
that.
no, I was surprised. So what do you think the correlation would be?
Sorry, one more time. It was
How old are you? And how many classes do you have left for your degree?
mm, like a weak positive, like a well, like the older you are, the less. I don't know. I want to say 0.8.
Yeah, it was actually almost 0.
Really?
Yeah, I was surprised. Now we only had a sample size of 5, but still, I was like,
Oh,
wow, 0?
huh.
Now it was 0.2, which is basically close to 0.
0.2. Gotcha.
0.2 is almost 0. Yeah, I was
Um,
like shocked.
yeah, that's interesting.
Yeah, I asked the students to come up with something they might be interested in. It was nice
Uh,
to have one with no correlation because I like to do the Lake Tahoe one, which has a severe correlation.
yeah, of course.
Yeah, it's my
Um,
favorite example. You've seen me do it before.
yeah. I wanted to ask you, do you think you'd have like some time to like answer like one or two of their questions? The
Sure.
the group that I'm currently like or have worked with, I guess.
Which group is it?
It's Marquette.
Oh, okay. I actually talked
Uh,
to her for about 45 minutes today.
Marquette, Jack, and I know she kind of she did mention that, but some of the stuff kind of like
Overhead.
flew over her head, and
Yeah,
she
there was
kind
a
of
lot.
wanted
Yeah.
yeah she kind of wanted
Mhm.
her group in on
Yeah.
the
Right. Well, the one thing that I stressed on it was dependent data.
dependent data. Yeah,
She was
I
gonna,
totally missed that. Yep.
she was going to say it was independent because we're talking about each town has 2 items. So
Yeah, yep. I don't know why I missed that, but yeah, it totally makes sense. Yep.
yeah.
Okay.
Yeah.
Let me can I just get them in this chat here or somehow?
Yeah, but if they're on Zoom with you,
No, they're in a Google meeting.
okay, so they can, I think they can do both Google Meeting and Zoom if they wanted to jump in.
They could do both. Okay.
I think so. They can't do Zoom and Zoom. I don't think you could double Zoom in the same computer.
No.
And when I double Zoom, I have 2 computers next to each other.
Okay, I am joining them now.
Mhm.
Hold on. Sorry, sir.
I might be able to join them if you tell me how. That's the other choice. It might be easier. If there's some kind of link that
Sorry,
I
what was that, Larry?
Oh, if there's a link you can give me, I can join them.
Okay, great. I'll do
If there's
that.
more, if you're all on the same, it's easier for me to switch.
Right.
But I have to know how to get in.
All right, give me 1 sec.
If you have a link to put in the chat, then that'll work.
Hey, Larry.
Yeah.
Here.
Okay, let me put it in.
I hope that works.
It should.
And I appreciate that so much, Larry. Oh, it's
Oh, I
okay.
may need to log out of Zoom
Okay, that's fine. Oh, are you gonna lose the link?
because let's see, let me ask to join. It says the camera failed because I think my camera's on Zoom. And I don't
Yeah,
know. Let's see.
that's
But
fine. We'll
the
just
camera's not
switch
that
over to
important.
that.
Yeah.
We'll just switch over to that.
Okay, so I see all of you. Do you see me?
Yes, you're there.
Okay, yeah, I don't think you can see me. How's it going? I'm on Zoom because I was actually teaching a class.
It's okay. I'll
So
talk to you
my
on later.
camera, I don't think my camera could double Zoom. I think that's the problem, is the camera's focused on one thing. But you can hear me.
Yeah.
Okay.
Yes.
Hey, Larry.
Yeah, thanks for
I've left the Zoom meeting.
Okay, so I'm gonna log out of my Zoom.